I bet you have wondered about black holes and singularities, especially how they are different and why black holes come in all shapes and sizes. It is a common point of confusion, and frankly, it touches on some of the most mind-bending concepts in physics. Let us demystify black holes and singularities together really quickly and figure out why some black holes have enormous event horizons while others are tiny. First, consider, what exactly is a black hole? Well, despite the name, it is not actually a hole in space. Instead, it is an incredibly dense object, a region where gravity is so strong that nothing, not even light, can escape its grasp. Imagine an object so compact that its gravitational pull becomes irresistible. That is the essence of a black hole, a true cosmic titan. Black holes primarily form from the remnants of massive stars. When a star much larger than our Sun exhausts its nuclear fuel, it can no longer support itself against its own immense gravity. The core collapses inward, compressing an unfathomable amount of mass into an incredibly small space, triggering a supernova explosion and leaving behind a black hole. To understand how nothing escapes, we need to talk about escape velocity. Every object with mass has a gravitational pull, and to break free from it, you need to reach a certain speed. For Earth, it is about 11.2 kilometers per second. Launch a rocket faster than that, and it is off to space. Slower, and gravity pulls it back down. Now, imagine a celestial body so dense that its escape velocity exceeds the speed of light itself. Since nothing in the universe can travel faster than light, anything, including light particles, photons, that crosses a certain boundary around this object is trapped forever. This crucial limit is what gives black holes their name and their mysterious reputation. At the core of every black hole, according to general relativity, lies a singularity. Picture this. It is not just a small point, but a theoretical point of infinite density and zero volume. All the mass of the black hole is compressed into this single, infinitely small location. It is where the known laws of physics, as we understand them, completely break down. This concept of infinite density at a zero volume point can be hard to wrap our minds around. It suggests that space and time themselves cease to have meaning at this extreme locale. While the singularity is often depicted as the bottomless pit of a black hole, it is truly an extreme mathematical construct arising from Einstein's equations. So, the singularity is the infinitely dense, infinitely small kernel at the heart of a black hole. But what about the edge of a black hole? The point of no return we just discussed? That is what we call the event horizon. It is a boundary in space-time, not a physical surface, but an invisible line of demarcation. The event horizon marks the exact distance from the black hole's center, where the escape velocity precisely equals the speed of light. Cross this boundary, and you are irrevocably committed to falling into the singularity, no matter how powerful your rockets or how fast you try to swim. It is a one-way door to the cosmic unknown. Imagine a river flowing faster and faster towards a giant waterfall. The event horizon is like the point in the river where the current becomes stronger than any boat can paddle upstream. Once you drift past that point, even if you paddle as hard as you can, the river's flow carries you inevitably over the falls. There is no turning back. The speed of light is the universal speed limit, approximately 299,792,458 meters per second in a vacuum. The event horizon exists because at that particular radius from the black hole's center, the space-time fabric itself is warped so severely that all paths, even those trying to move outwards at the speed of light, actually lead inward. So, we have the singularity, an infinitely small, infinitely dense point. And we have the event horizon, the boundary around it, beyond which nothing can escape. This brings us to the core of our original question. If all singularities are infinitely small and have infinite gravity, why would not the event horizons they produce be identical in size? It is a really insightful question, and the answer clarifies a common misconception. The infinite gravity associated with the singularity refers to the theoretical intensity at that single point. However, The event horizon is not just about the singularity itself, it is about the total mass enclosed within that singularity. The key here is that while the singularity itself is considered a point, the amount of stuff, the mass, that collapsed to form that black hole can vary wildly. Think of it this way, a tiny pinprick is still a pinprick, but one pinprick could be the result of a small needle and another a giant nail. The point is the same, but the source is different. And this leads us to the fundamental principle. The size of a black hole's event horizon is directly proportional to its mass. More mass means a larger event horizon, less mass means a smaller one. It is a direct relationship governed by precise mathematical laws, mainly Einstein's general relativity. The more mass you pack into that tiny point, the stronger the gravitational field it creates around itself. This stronger gravitational field extends further out into space, meaning the point at which escape velocity equals the speed of light, the event horizon, will also be further away from the singularity. This relationship is described by the Schwarzschild Radius, named after physicist Carl Schwarzschild. It is a formula that tells us the radius of the event horizon for a non-rotating, uncharged black hole of a given mass. Essentially, it is the critical radius where an object becomes a black hole if all its mass is compressed within it. The Schwarzschild radius increases linearly with mass. Double the mass of a black hole, and you double the radius of its event horizon. This is why black holes can have event horizons that range from just a few kilometers across for stellar mass black holes to billions of kilometers for supermassive black holes. Let us use an analogy. Imagine placing different-sized bowling balls onto a stretched rubber sheet. Each ball creates a dent in the sheet. The center of each dent is like our singularity, a point of extreme curvature. But the size of the dent and how far its influence reaches depends entirely on the mass of the bowling ball. A small bowling ball makes a small dent. Its gravitational influence, how far the sheet is significantly curved, extends only a short distance. In this analogy, the edge of that significant curvature where escape becomes impossible would be a small event horizon. Now, place a much larger, heavier bowling ball on the same sheet. It creates a much deeper and wider dent. Its gravitational influence extends much further, and the point of no return on our rubber sheet analogy would be much larger. This larger influence directly corresponds to a larger event horizon for a more massive black hole. So, while the singularity itself remains a theoretical point of infinite density, the amount of mass that point contains is what determines how much spacetime around it is bent. And how much spacetime is bent determines the size of the event horizon. It is not about the singularity's inherent strength being different. The singularity is like the source code of the black hole, defining its core property. But the event horizon is the manifestation of that core, scaled by the total mass. The singularity does not change its point-like nature, but the field it generates changes based on the mass feeding it. Think about it like two magnets. Both have a tiny, almost point-like source of magnetism within them. But a small fridge magnet has a much weaker magnetic field that only extends a short distance, whereas a giant electromagnet has a massive field reaching far wider. The point of origin of magnetism is tiny in both, but the scale of the magnetic effect is vastly different. This brings us to the different types of black holes we observe. The most common are stellar mass black holes, which are typically 5 to 100 times the mass of our Sun. These are the remnants of massive stars collapsing, and they have event horizons only a few tens to hundreds of kilometers in diameter. For example, a black hole with a mass 10 times that of our Sun would have a Schwarzschild radius of about 30 kilometers. That is roughly the size of a small city, like London. Pretty small, considering it contains the mass of 10 suns. Then, we have supermassive black holes. These gargantuan objects reside at the centers of most galaxies, including our own Milky Way. They can range from 100,000 to tens of billions of times the mass of the Sun. Their event horizons are proportionally enormous, spanning millions or even billions of kilometers. Sagittarius. A. The The supermassive black hole at the center of the Milky Way has a mass of about 4 million suns. Its event horizon spans approximately 12 million kilometers, which is large enough to comfortably fit several stars in our solar system's orbit. And there are also intermediate mass black holes, bridging the gap between stellar and supermassive. These are thought to be hundreds of thousands of times the mass of the Sun, with event horizons sized accordingly. Their formation mechanisms are still an active area of research. The existence of these vastly different sizes, each with its own point of no return, beautifully illustrates how the total mass dictates the geometry of spacetime around the singularity. The singularity itself may be a consistent theoretical point, but the gravitational field that projects into the universe varies with the fuel it consumes. Ultimately, the point is that the singularity, while theoretically infinite in density, is a concept primarily describing the internal state. The event horizon, however, is an observable boundary, a macroscopic effect of the black hole's total mass on the surrounding spacetime. Our current understanding of physics, particularly general relativity, provides an excellent description of gravity on large scales, successfully predicting phenomena like black holes and their event horizons. However, at the singularity itself, where density is infinite and volume is zero, general relativity breaks down. This is why physicists are eager to develop a theory of quantum gravity which would unify general relativity with quantum mechanics. Such a theory might offer a more complete picture of what truly happens at the singularity, perhaps revealing it is not quite an infinite point as we currently imagine. The event horizon, on the other hand, is a much better understood concept. It is a boundary we can calculate and even, in a way, see through its effects on light and matter surrounding a black hole. It is a real, measurable consequence of a black hole's mass, even if the interior remains a mystery. What becomes clear is that the difference between a black hole and a singularity is one of scale and definition. A black hole is the entire region of spacetime from which nothing can escape, defined by its event horizon. The singularity is just the incredibly dense theoretical point at its very center. To put it simply, think of it this way. The singularity is the infinitely heavy seed that creates the black hole. But the event horizon is the garden of gravitational influence that grows around that seed. The larger the seed, the more mass, the larger the garden will be. So, when we talk about black holes of different sizes, we are referring to the varying sizes of their event horizons, not the singularity itself. The singularity remains a point, but the gravitational field it produces, due to the immense mass compressed into it, determines the reach of its event horizon. The biggest lesson: do not confuse the infinitely small theoretical core, the singularity, with the measurable, physical boundary that defines the black hole's influence, the event horizon. The latter's size is a direct consequence of the former's total mass. What this boils down to is that a black hole's size is not about the singularity, but about how much mass has been crammed into that singularity. That mass then creates a gravitational field so powerful that the point of no return, the event horizon, extends further out into space. Ultimately, understanding the difference between the singularity and the event horizon, and how mass plays a pivotal role in the latter's size, deepens our appreciation for these enigmatic cosmic phenomena. They are not just holes, but extreme regions where gravity reigns supreme, dictating the very fabric of space and time around them.